The B-2 Spirit isn't just another aircraft in the United States inventory. It is not simply a bomber. It's a precise, mathematically engineered solution to a highly specific problem: how to completely eliminate an adversary's ability to respond to an airstrike. In this explainer, we're going to conduct a clinical teardown of the physical systems that make this level of invisibility an operational reality.
To understand exactly how it achieves this, we'll examine the mission that proved its design, followed by the 4 structural pillars of its engineering. First, the unseen strike. Second, flying wing architecture. Third, radar cross-section management. Fourth, exhaust heat suppression. And finally, the strategic calculation.
Part 1. The Unseen Strike, Operation Allied Force. Up into the spring of 1999, the engineering theory behind the B-2 remained largely untested in major combat, but this conflict served as the ultimate undeniable proof of concept for the aircraft's stealth capabilities. On the first night of the operation, 6 B-2 Spirit bombers departed from Whiteman Air Force Base in Missouri. Their mission profile demanded a grueling 30-hour continuous flight. They crossed 2 oceans to penetrate Yugoslav airspace, which at that time was defended by one of the most sophisticated, densely packed, integrated air defense networks in Europe.
The operational reality of that night remains terrifying for air defense operators. You see, the Serbian network relied heavily on advanced Soviet-supplied S-125 Neva missile systems. Their radar installations covered every major approach corridor. This network detected absolutely everything else that entered its coverage zone: F-15s, F-16s, EA-6B electronic warfare aircraft. But against the B-2, the network registered 0 radar detections. The bomber delivered its payload and exited the threat zone entirely unseen.
Part 2. Flying wing architecture and aerodynamic instability as a design choice.
To understand how an aircraft physically vanishes from a radar screen, we have to examine the radical airframe itself. Every surface that protrudes from a conventional airframe creates aerodynamic drag, but more importantly, it creates a radar return. A conventional B-52 bomber features a fuselage, a massive tail assembly, and external engine pods. All of this results in a composite radar return of approximately 100 square meters. On a radar screen, it effectively appears as an object the size of a small house. But the B-2's continuous blended wing, spanning 172 feet, eliminates those protruding structures entirely. This reduces its radar return to precisely 0.1 square meters.
Now, the engineering cost of eliminating those radar-reflecting tail assemblies is severe aerodynamic instability. Without a tail to provide pitch and yaw stability, the airframe inherently wants to tumble out of control. A human pilot simply cannot physically react fast enough to correct this. Because of this, controlled flight is only made possible by a quadruplex digital fly-by-wire system. This flight control computer makes thousands of micro-corrections per second, adjusting control surfaces faster than the human nervous system can process. The pilot directs the mission, but the computer physically flies the unstable wing.
Part 3. Radar cross-section management, surface geometry and coding.
Achieving a radar cross-section the size of a large bird requires a second engineering pillar: manipulating how electromagnetic energy behaves against the aircraft's skin. The entire external surface is coated in what is known as iron ball paint. This is a highly specialized composite that induces a magnetic field within microscopic iron particles the moment it makes contact with hostile radar energy. Instead of reflecting the signal back to the enemy radar dish, the coating physically converts that electromagnetic energy into thermal energy. The radar wave is absorbed and quietly dissipated as heat.
Maintaining this stealth profile, however, enforces strict operational constraints. The surface geometry features extremely specific deflection angles designed to scatter any unabsorbed radar away from the source. Furthermore, the RAM coating itself is highly sensitive to temperature, humidity, and physical wear. After missions, ground crews have to conduct exhaustive surface inspections. Any damaged sections are stripped and recoated completely by hand. And to prevent any aerodynamic protrusions that would ruin that perfectly cultivated radar cross-section, the B-2 must carry all of its ordnance internally. 2 internal weapons bays conceal up to 40,000 pounds of munitions, leaving the exterior completely smooth.
Part 4. Exhaust heat suppression, managing engine signatures.
Radar is not the only threat in the sky. Modern air defenses utilize highly sensitive infrared tracking. Masking the B-2's 4 General Electric F118 jet engines requires highly specialized physical geometry to manage a dual threat. First, the rotating compressor faces inside a jet inlet act as giant radar reflectors. The engineering solution here is an S-curve internal duct. The inlets are positioned on the upper surface of the wing, hidden from ground radar, and the duct curves sharply. Radar entering the inlet strikes the interior walls and is absorbed before it can ever reach the compressor. The second threat is the infrared exhaust plume. Hot gas exiting a jet engine is a beacon for heat-seeking missiles. The B-2 solves this by bleeding cool bypass air into the hot engine exhaust. This mixed air is then expelled through wide slots in the trailing edge of the wing rather than through standard circular nozzles. This process dramatically lowers the temperature and disperses the remaining heat signature across a wide flat area.
Part 5. The strategic calculation. The absence of action.
These integrated engineering systems don't simply make the aircraft hard to hit, they fundamentally rewrite the established rules of conventional air defense. Conventional air defense relies entirely on a rigid, linear sequence. Step 1. Detect. A radar identifies an incoming target. Step 2. Track. The fire control system classifies the threat and calculates its speed and altitude. Step 3. Engage. A surface-to-air missile is launched on an intercept vector. The crucial point here is that against the B-2, Step 1 never initiates. Because the radar return is too small to trigger a threat classification, the fire control system never even wakes up.
Reviewing the operational timeline of Operation Allied Force cements this reality. Against the conventional bomber, the detect, track, engage sequence requires a window of 30 to 90 seconds. Because the B-2 bypassed this window entirely, its operational success was obsolete. During the 1999 conflict, B-2 crews flew 49 missions. They delivered 11% of all ordnance dropped during the entire campaign. Operating in airspace actively defended by capable, non-peer adversary radar systems, they concluded the operation without a single detection. But the physical engineering is only part of the equation. During that very same conflict, an American F-117 stealth aircraft was shot down. An air defense operator deduced its location not through direct radar detection, but through patient observation of its predictable flight timing patterns. The lesson was immediate and severe. Physical stealth must be paired with flawless operational discipline. The B-2 relies on highly unpredictable ingress routes, randomized flight corridors, and absolute communication silence during execution to ensure the physical engineering is never compromised by human predictability.
The B-2 spirit exists at the precise intersection of four integrated systems: the tailless flying wing, the radar-absorbent coating, the S-curved engine inlets, and the heat-dispersing exhaust slots. Each solves a specific detection problem. None are sufficient on their own, but together they create an undeniable tactical reality. They ensure that the first indication an adversary has of an incoming strike is the sound of explosions on the ground. And by the time the enemy air defense operators understand what has happened, the aircraft was already gone. This forces us to ask a critical question. How will conventional air defense networks ever adapt to a threat they fundamentally cannot see?